Okay, I can protect my voice. Can everybody hear me?
Yes.
Yes? Okay, welcome to Spacecraft Preliminary Design. I'd like to thank you for being here today. This will be the first and only time I'm going to ask our panelists to introduce themselves. We have 4 presentations, so.
Good afternoon. Actually, good morning, sorry. I'm Jacopo Gentilini. I'm a professor here at Embry-Riddle. My specialty is robotics, so I will help as I can the teams to succeed.
Good morning, my name is Jacob Alder. I'm an Embry-Riddle alum. Spent about the last 4 years in industry working on military rocket systems, and that's what
Morning, my name is Scott Blue. I'm retired military. I spent my whole career essentially working on classified military space programs.
I'm George Carlisle. I'm from JPL, and I'm an astrodynamicist like Kayla.
I'm Kayla Martin. I'm a faculty member here, in case you don't know me, but I've had most of you, so you probably should.
At this time, I'll pass it over to Nick Liapas, who will start us off on our first project.
Thank you, Dr. Benavides. Hello, everyone. Good morning. My name is Nicholas Lapis, and I'm the project manager of Imperium Space, and this is the preliminary design review of the Attitude Control and Deployment Concept, ACDC. I'd like to take a quick moment to introduce our assistant project manager, Adam Scott. So today, we'll start off by talking about the design team layout, then we'll talk about the mission concept, and then we'll talk about the ACDC System of Systems definition, then we'll go into the gimbal system definition and validation, then we'll go into the satellite system definition and validation, then go back into the ACDC System of Systems validation, and then conclude with some programmatics. So the design team layout is that we have the project manager, then we have 2 teams, the gimbal team and the satellite team, both with 3 members each, and then we have 2 system integrators, and then an assistant project manager. So at the beginning of the semester, we were given the task of designing a satellite that can determine and control its attitude, as well as deploy different sized CubeSats towards a target individually of each other. And it should be mounted within a 3-axis gimbal system. The target area is a sector of a ring with inner radius of 2.75 meters and an outer radius of 3.25 meters, with a total area of 3,750 centimeters squared. The diagram above, the black rectangle, is our system in the center, and for size comparison, our target is in red. And for our mission validations, we should be able to deploy our CubeSat, and the entire CubeSat should land entirely within that target. So this is a simulation of our system. So this is the first mission configuration. It's where it will deploy 3 1U CubeSats. So at the beginning of this mission, we will have the system in the center of that ring. We will click the button to toggle it on, and we will have 10-second delay before the system will actually perform its mission, at which time it will start to spin up to approximately 0.5 to 1 revolution per second about all body axes of the satellite, and then it will control its attitude and restabilize in order to deploy the first CubeSat. Once it deploys the first CubeSat, it will restabilize itself in order to launch the second, and then restabilize again in order to launch the third. Once the third CubeSat is deployed from the system, it will shut off and the mission will be over. So that was the first mission configuration, where we launched 3 1U CubeSats. This right here is a 1U CubeSat. It's 10 centimeters by 10 centimeters by 10 centimeters. We have other mission configurations. Our second mission configuration is that we can deploy a 2U CubeSat and then a 1U CubeSat. A 2U CubeSat is 20 centimeters long. It's like 2 of these stacked on top of each other. And then the third mission configuration is that it will launch a 1U CubeSat and then a 2U CubeSat. And then the fourth and final mission configuration that we will perform is that our system will launch a single 3U CubeSat, which is 30 centimeters long. So now I'd like to hand it off to our System Project Manager, Adam Scott, to talk about the System of Systems definition.
Thank you, Nick. Hello, my name is Adam Scott. I'll be going over our System of Systems definition. First of all, I'd like to introduce our integration team, Ryan Burns and Jesse Ives. So to start off, we have our overall System of Systems, the Attitude Control and Deployment Concept, or ACDC for short, consists of the satellite system mounted within the 3-axis gimbal system. Here we have our design structure tree. So a design structure tree is basically how our project is broken down into systems, subsystems, and individual components. At the top of the tree, we have our ACDC, System of Systems, and that is broken down into 2 systems, the gimbal system and the satellite system. The gimbal system consists of 4 subsystems: the gimbal base, the outer ring, the inner ring, and the bearings. The satellite system consists of 5 subsystems: satellite structure, CubeSat-deployment, attitude determination, attitude control, and the electrical subsystem. And each of those have components underneath them that will be discussed in more detail later on in the presentation. Here we have a CAD rendering of our overall system of systems. As you can see, we have a satellite mounted within the 3-axis gimbal. And I will actually go over and show you our mock-up. This is approximately a 1-to-1 scale model of our actual system that we will be fabricating in detail next semester. We have our gimbal base, which supports the whole structure. We have our outer ring, which provides the first degree of freedom of rotation. We have the inner ring, which provides the second degree of freedom. And we have the satellite system mounted within the inner ring with a shaft to provide the third degree of freedom for rotation. Also, as Nick mentioned earlier, we have for the first mission configuration, we have 3 1U CubeSats. So those will be mounted within a CubeSat launcher mounted in the middle of the structure. So for the first mission configuration, 3 of these would fit in here with divider plates in between them. And that CubeSat launcher can be adjusted for each different mission configuration. Here we have a CATIA rendering showing you what we have on the mock-up here. We have our CubeSat launcher mounted in the middle of the satellite system. We have 12 microthrusters mounted around the satellite to provide attitude control. Hence these little cubes right here. We have 12 of them, 4 on each face, and then 4 on the top, and so 2 on the top, 2 on the bottom. We also have solar panels mounted around the satellite. The purpose of the solar panels is to help determine our attitude in conjunction with 2 IMUs that will be mounted inside the satellite. So with the IMUs of the solar panels, we will be able to determine our attitude. Here we have a CAD rendering of just the bare structure of our satellite. So we have a satellite frame, which will be made out of aluminum and welded together. We have 2 mounting plates in the middle of the satellite. The purpose of the mounting plates is to provide attachment points for the rest of the subsystems. Here we have a CATIA rendering showing the inside of the satellite with our propulsion. We have 2 compressed gas tanks, which will be compressed air. Again, you can see the microthrusters around the satellite. And we have a pressure regulator to drop down the pressure from the tanks to a manageable pressure for the solenoid valves, which I'll go into detail in this slide. We have solenoid valves connected to branch T's, which will connect all our hosing from the pressure regulator in the tanks. Now I'd like to pass the presentation on to Gavin Hofer, who will be going over our gimbal system definition.
Thank you, Adam. Hello, everyone. My name is Gavin Hofer, and I'm the Gimbal System Team Lead for Imperium Space. I'd like to introduce our team members, Drew Takeda and Jacob Turner. So the objective of our gimbal system is that the gimbal system should allow 3-dimensional rotation of the satellite, and that the gimbal system should physically support the satellite system. Our gimbal system is made up of 3 main subassemblies, which are the gimbal base, the outer ring, and the inner ring. Together, these will physically support the satellite system while allowing 3-dimensional rotation. The way these interface are through a bearing shaft, which goes through a bearing, and then the shaft attaches to a flange mount, which you can see the bearing is mounted in this plate, and then the flange mount is on the inside component. So here's a close-up of how the bearing attaches to the gimbal base. So what you have here is a steel plate, which is welded onto the gimbal base structure. That bearing is press fit into the hole in the steel plate. Then the bearing shaft is slid into the outside, in from the outside through the bearing. This wider diameter section of the bearing shaft will press up against the outside of the bearing, and the bearing will be held on the other side using a shaft collar with a set screw. Together, these will transmit any axial loads from the shaft to the bearing. Here's a close-up of how the bearing and shaft attach to the gimbal rings. It's very similar to how it attaches to the gimbal base, except in this case, the plate is attached using bolts rather than welds. That's because the bearing plates are made out of steel, while the bearing gimbal rings are made out of aluminum. And here's how the flange mounts attach to the gimbal rings. It's also attached using bolts, and then the bearing shaft is slid into the collar, and it's attached with 2 set screws to secure it in place and transmit any expected loads. So our gimbal system has one requirement, and that's that the gimbal system shall withstand all dynamic loading, while the satellite system has an angular speed of greater than or equal to 1 revolution per second about all axes. The reason we chose this value is because our primary objectives state that the satellite system should be raised to an angular speed of between 0.5 and 1 revolution per second about all axes during the mission. And we wanted the gimbal system to withstand all dynamic loading throughout this entire range. With that, I'd like to pass it off to Drew Takeda to talk about gimbal system numerical validation.
Thank you, Gavin. Hi, my name is Drew Takeda, and I'll be going over the gimbal system numerical validation. So in order to validate our requirement for the gimbal system, we had to conduct structural analysis on the overall gimbal structure, and we used a finite element analysis model using analysis system, also known as ANSYS. In this ANSYS model, we applied the maximum loads that the gimbal system will undergo throughout the duration of the mission. We also analyzed fastener shear, bearing plate failure, and tear-out failure. We validated these by conducting hand calculations. So this is a first orientation of our ANSYS model. For this, we used a bind mesh. As far as the constraints and loads, we constrained the bottom of the gimbal base in all degrees of freedom, and we applied a 538 Newton load on the shafts of the inner gimbal ring. This 538 Newton load we got from the simulation, and we added in a factor of safety of 1.5. For the results for the first orientation, we found the maximum von Mises stresses. The maximum stresses occurred in the bottom corners of the gimbal base and in the shafts of the inner ring, as well as the outer ring near the bearing plates. So the maximum stresses found were about 83 megapascals in the gimbal base, 124 megapascals for the shaft, and about 27.5 megapascals for the gimbal rings. With the 836 mild steel and the 6061 aluminum materials, we found that we had a margin of safety of about 3 for the gimbal base, 2 for the shaft and gimbal rings. Also note that the deformations shown in the ANSYS model are not to scale. If we had them to scale, they would be imperceptible. So now I'll show you the second orientation that we had for our ANSYS model. And once again, we used a fine mesh size for this. And once again, we used the same constraints. We constrained the bottom of the gimbal base in all degrees of freedom and applied the 538 Newton loads on the shafts of the inner gimbal ring. As far as the result for the second orientation, we found that the maximum stresses in the gimbal base was about 50 megapascals and 223 megapascals for the shaft and about 32 megapascals for the gimbal rings. Based on the material properties, we found that the margins of safety to be about 4 for the gimbal base, 0.12 for the shaft, and 1.73 for the gimbal rings. Note that these margins of safety are relatively high, but this is due to the availability of materials. And also, we wanted the gimbal base to be heavy so that it wouldn't translate or rock when the satellite was in operation. As far as fastener shear, we looked at our 1/4 inch grade 2 steel bolts, and we found the margin of safety to be about 9.37. And for the plate bearing failure and the tear-out failure, we found the margin of safety to be about 1.5 and 1.9. This included a factor of safety of 1.5 added to the load and a bearing factor of 2. And this was analyzing the 1/8 inch thick 6061 aluminum tubes. Now I'll hand it off to Jacob Turner to talk about the gimbal system experimental validation.
Thank you, Drew. I'm Jacob Turner, and I'll be going over the gimbal system experimental validation. So to experimentally validate the gimbal, we'll first spin the satellite in this configuration to approximately 1.5 revolutions per second about the satellite axis. We'll then spin the outer ring to approximately 1.5 revolutions per second, and doing this will actually cause the inner ring to rotate due to gyroscopic effects, so the whole gimbal will be rotated in the test. The IM view on board the satellite will be on and recording data throughout the test, and this data will be analyzed afterwards to see that the satellite met the minimum requirement, that is 1 revolution per second about all 3 satellite body axes. After the test, the gimbal will be structurally analyzed to make sure that the bearings were able to support the dynamic load as well as the gimbal rings, base, and axles. Here's a video that shows real time what it looks like with the speeds that I've stated. Notice the gyroscopic effects causing the inner ring to rotate even though no force was applied to it prior. And that's the validation of the gimbal system. On the half Consuelo Wells up to talk about the satellite system. Thank you.
Thank you, Jacob. My name is Consuelo Wells, and I am our satellite system team lead. I'd like to take a moment to introduce the rest of my team members, Oliver Nahida and John Lowe. Thank you. So this is our satellite system. As you can see, it is mounted within the gimbal rings over on our mock-up. The satellite system's purpose is to be able to control and determine its attitude, as well as launch CubeSats in different configurations to a specified target. It does this by having a few different subsystems. So the first subsystem I'd like to introduce is the launcher subsystem. So as you can see here, in the middle of the satellite is the launcher subsystem. It will have 3 springs within it that act as our launch mechanism, as well as removable divider plates. The divider plates allow us to accommodate different launch configurations that fulfill our primary objectives. And when the CubeSats are loaded within the launcher, they are kept in place by 6 lock-style solenoids. The solenoids are kept on the top and the bottom of the launcher, and once they are activated, they retract and release the springs and the CubeSats to their specified launch target. This is just another introduction to those lock-style solenoids, just to give a better idea of what they look like. They are usually out, as seen in the picture behind me, and when they are activated, they retract. So next, I'd like to go over the structure. The structure is made up of 1 inch by 1 inch 6061 aluminum tubing. The structure also has 2 mounting plates for various mounting needs. So we have our tank brackets, as well as the lock-style solenoid holes that they would be mounted within, and a place to mount any electronics that we'll need throughout the mission. So that brings me to our propulsion and attitude control system. This system is made up of 2 3,000 psi compressed air tanks. These air tanks have an output pressure of 300 psi, which we need to step down to a more manageable 180 psi through a pressure regulator. Pressure regulator is then routed to T-joints that go to valve solenoids. There are 6 valve solenoids, and these connect to our 12 microthrusters around the entire satellite. The microthrusters are positioned in such a way that they are maximizing our moment arm, as well as connected via the valve solenoids to be equal and opposite. They have an exit velocity of 1.57 Mach, and they also have 2 newtons of thrust. That brings us to our attitude determination system. The attitude determination system, as said by Adam, is made up of solar panels, which are these blue squares on the mock-up. They are all over the satellite, including the end plates, to minimize any chance that all of them will be shadowed. And this is because the way we will determine our sun vector is by analyzing the voltage of any of the solar panels at any given time, and whichever has the highest voltage is facing the sun. The other way we'll do this is by having 2 IMUs mounted opposite each other inside the satellite. They are mounted opposite each other around the rotational axis of the satellite, which negates any rotational effects and allows us to get our gravitational vector and determine our attitude. I'd like to briefly go over our satellite system requirements. The satellite shall be able to raise its angular speed to between 0.5 and 1 revolution per second. It shall also be able to have an error in roll, pitch, and yaw of less than 40 degrees, 15 degrees, and 7 degrees respectively. And it shall also be able to deploy all CubeSats to between 2.75 and 3.25 meters away from the satellite system. Now I'd like to give it off to Oliver Nahida to go over our numerical validation.
Thank you, Consuelo. Good afternoon. I'm Oliver Nahid, and I'll be discussing the validation of our system level requirements for our satellite. The first requirement we validated was the spin-up requirement, which is an angular speed of between 0.5 and 1 RPS in each axis. We made a Simulink model to validate this, and we found from the data that the Simulink model gave us that we reached a maximum angular speed of 0.5 in the x-axis, 0.7 in the y-axis, and 0.72 in the z-axis, which were all within our bounds. The next requirements that we validated were our error in attitude requirements, which were to be less than 40 degrees in roll, less than 15 degrees in pitch, and less than 7 degrees in yaw. We validated this with the same Simulink model, which was the source of those videos you saw earlier. With the data we gathered, we found that our error in roll was 4 degrees, our error in pitch was 4 degrees, and our error in yaw was 2 degrees. The errors in pitch and yaw are the most important because they will have the greatest effect on the trajectory of our CubeSats when they are launched. The next requirement we validated was our launch distance requirement, which was that the CubeSat should land between 0.275 meters and 0.325 meters. We validated this with a combination of hand calculations to first determine the characteristics of a spring we would need to deliver the impulse to the CubeSats to traverse a distance of 3 meters at a 45-degree launch angle. And then we found a spring that either exceeded or met those requirements. We then used those characteristics in our Simulink model, and we found that we landed in the 3-meter target. We made it 3 meters so that if we fell short, we would still land within the target, and if we fell a bit far, you would land within the target. Next, I would like to bring up John Lowe, who will discuss the validation procedure and our design metrics.
All right. right, thank you very much, Oliver. My name is John Lowe. I'm going to be going over the experimental validation procedure for the satellite system and some additional design metrics. So we have 3 tests planned to validate all of our requirements. First up, we have the launch test, in which we will be placing the satellite in a test stand. From there, we are going to individually launch 1U CubeSats, and this will validate that we can hit all of our targets. Next up, we have the spin-up test, in which we will be spinning the satellite up inside the gimbal to make sure that we can meet those requirements. And finally, we have our attitude test. This is going to be the most complicated system level test, as it involves basically performing a full system of systems test. However, we will not be deploying CubeSats. What is entailed in this test is we will spin the satellite up and then allow it to control its attitude to a desired orientation so that we can then be able to launch CubeSats in our full system of systems test. So here we have a structural analysis of the satellite, and while it doesn't directly validate any satellite system level requirements, we did believe that it was important to mention in this presentation that we have performed analysis. So we performed a coarse mesh analysis in ANSYS Workbench on the key structural elements. The reason we have not yet performed a more refined mesh on a more complete model is because ANSYS actually crashes when we try to do that due to the output file size. So in detail design, in the early stages, we are going to work on performing a more complete model and a more advanced refinement. However, as the results will show shortly, we do not expect there to be any problems. So for the loading, we applied 400 newtons of force in the positive Z direction on the satellite, specifically on the shaft mount. This value was taken from the Simulink model that our prior videos and analysis was based on. And for the constraints, we used a symmetrical constraint in the middle of the satellite, which is why it appears that there are 2 halves to the satellite here. So for our results, we found a maximum stress of 31 megapascals. The material we're using for these plates is 5051 aluminum. So we have a yield stress of 193 megapascals, giving us a margin of safety of over 5. While this does seem over-designed, material selection and thickness was heavily based on availability of materials and what we can buy. And just for a little clarification, the location of those stresses is right here underneath the shaft collar mount. So in regards to our power consumption, here we have all of the electrical components we're currently planning on using. We have an Arduino DUI, which we will be using as our microprocessor to handle all of our onboard computer needs and onboard data processing. We have a 16-channel relay that we're going to be using in conjunction with the Arduino to fire all of our solenoids at the appropriate time. We have our 6 solenoid valves, which allow us to control our thrust. We have the 6 lock-style solenoids, which will keep the CubeSats in place until we are ready to launch them, and the 2 IMUs that we'll be using for attitude determination. So the total power consumption is a little over 1 watt-hour, which when converted is 113.5 milliamp hours. This, compared to our 2200 milliamp hour battery that we currently have selected, is significantly lower. So next semester in detail design, we're going to look for a lower capacity battery that will hopefully save us not only cost, but additionally on weight. I'd now like to pass it off to Jesse Ives to talk about the system of systems validation.
Thank you, John. Hello, my name is Jesse Ives, and I'll be discussing the system of system validation. All right, to start off with, I'm going to go over the system of system requirements. So the first requirement is that the satellite should have a rotational velocity of 0 at mission commencement. So following mission commencement, the system of systems will spin up the satellite to between 0.5 and 1 revolution per second about all axes. And then the system of systems will also be capable of deploying the CubeSats to a distance of between 2.75 and 3.25 meters. In addition, the system of systems will be able to complete all 4 mission configurations in a time span of 180 seconds per mission. Now moving on to the numeric validation of the system of systems. So in order to numerically validate the angular speed requirement, we used the Simulink model of our system of systems, and we ran it through the mission and determined that during the spin-up portion, the satellite attained a rotational speed about every axis between 0.5 and 1 rotation per second, as you can see here. Next, we validated the launch distance requirement. We did this by using hand calculations to determine that the spring we had chosen was capable of launching the CubeSats to our desired target distance of 3 meters, which is halfway between the 2.75 and 3.25 meter requirement. As a factor of safety of 0.92. And finally, for the mission time requirement, we validated this by having the Simulink model run through all 4 mission configurations in completion from start to finish. And as you can see here, all 4 missions can be completed in well under the 180-second required time. And I'd like to hand it back to Nicholas Lapis, who will go over programmatics.
Thank you, Jesse. Now for some programmatics. So for this entire project, we were allocated $1,600, of which we spent $50 on this mock-up. Another $50 we are going to spend on another mock-up. Another $50 we will spend on program administration. And then we also set aside 15% just in case we run into for a contingency plan, just in case we run into some problems in detailed design next semester. So that leaves us with a total budget for this project of $1,210, of which we spent $1,132, leaving us with $78 remaining. The hours for this project, we spent about a third of the hours in class in professional development. Another third we spent out of class working on design, which is engineering column, and then everything else, another third for everything else, leaving us with a total of 2,156 hours. So lessons learned during this project is that requirements drive the design process, not the other way around. Another issue is that to avoid single point failures, which means that don't have one person working on one thing, because then if that person does something wrong, then there's no one to validate that, and they're the ones that's the expert on that field. And then if they can't come to class or anything, then you can't make any progress on that section. And also, communication is key. So we'd like to thank Dr. Julio Benavides and Dr. Patrick McElwain on their contributions to this project during this entire semester, as well as everyone else listed above. And now I'd like to invite the rest of my team up for some questions.
Just want to say good presentation. I like your cardboard mock-up. It looks like cardboard. I just had a couple of questions more regarding, you probably haven't thought about these, but more like comments for your testing situation next semester. Are you planning on depleting both of your canisters of air equally, or are they planning on depleting one and then the other?
Yeah, so the air canisters, they will lead into a T-joint into the regulator, so both of them will be depleted equally.
Okay, that's a great idea. And when you're doing your attitude test, are you including the CubeSat mock-ups in that, or is it just spinning without them?
Yes, the simulation.
No, your actual test. Or have you not done that?
Oh, the actual test for the satellite?
Yes.
The satellite will spin up with CubeSats inside,
okay,
because that's what it will have to do during the mission.
Got it. And so you are planning on spinning it up by hand to 1 RPM?
Yes. So The reason why we want to do that is so that we don't have to, if something goes wrong, we don't have to refill the air canisters after every single test, because that does take time. So also the mission will not require all of it, all of the air that we will have. We left a factor of safety of 1.5.
And then in terms of how will you know that you get to the right speed? Are you gonna have a transmitter with your OBC, or?
No, we will not have any transmitters. What will happen is the system will be completely autonomous during the mission, and then afterwards we will gather the data and inspect it later.
Okay. And then are you planning on having a ambient lighting or a single point lighting for your solar panel determination?
So we're planning on testing everything outside behind AXFAB. So we will be using the sun.
Okay.
Does that answer your question?
Yes, it does answer your question. But whether or not the quality of your solar panels that you will be able to acquire will be able to, you might want to have a light to shine on it.
Okay. Thank you for your feedback.
Yeah, especially if it's not sunny.
Yeah, I'll just add your presentation was very good. I'm intrigued by this attitude control system because you've got two IMU units that you can use by themselves to determine the attitude. So I'm not sure what additional information or why is it important for you to also determine the sun's direction.
So in order to determine the attitude of our satellite, I'll show you right here. If we could determine the gravity vector, the satellite itself can be oriented anywhere in this 360 degrees, but we need it to face towards the target, so we need two vectors in order to determine our attitude. Does that answer your question?
Okay, except that I mean, my understanding, I'm not an attitude control expert, but my understanding of IMUs is that an IMU is sufficient on its own to completely determine your attitude in space in 3 axes. So I guess I'm missing something here about what additional information is being gained from the sun. And I'll tell you, it's based on my experience where we either use celestial sources to determine attitude. So in that case, we'll use the sun and stars. And those two vectors together will give us an attitude. Or we just use the IMU. So unless, I guess I'm just not, maybe I just need to read your attitude control section more completely to understand what so
it's all right.
Like you couldn't do this at night, for example. Is that what you're saying?
We would not be able to perform this at night. I would like to pass this off to John Lowe to explain further.
So I think the best answer to your question is that we are not going to be using the full sensor package on the IMUs. We are only planning on using the accelerometers and the gyroscopes for angular speed measurements.
Okay.
So as a result of that, we need the second set of outside vectors, which is why we have the solar panels.
That answers the question. You've got a dark guy working.
So, really good presentation. I liked the format. You guys did a great job up there going through the presentation in a concise and logical manner. A couple of questions. Why solar panels instead of sun sensors?
The main reason why we chose solar panels is because of cost. Yeah, because of cost issues. Does that answer your question?
Yes. And when you do the launch tests, you have given accuracy requirements, if you will, for how accurately you can point the spacecraft to the location that you want to
Yes, sir.
eject the canisters. Are you going to do the tests for ejecting the canisters with the off-axis, the greatest off-axis position of the spacecraft that you will allow in order to make sure that you still hit the target area?
Yes, that would be great. We plan to do that because if we set these tolerances in our system and then we don't test to make sure that that actually works, then that's not something that we should do. So.
Okay. I just want to make sure you were doing it that way. When you talked about reading the RFP or reading the requirements,
Yeah.
was there some specific issue that came out of that? Because that's actually a really good lessons learned.
Yeah, so if you don't read the RFP fully right away and then you start going out into the session and you start brainstorming on your system, and then you think that you come up with a really great system, and then you go back and reread the RFP later and you find out that it doesn't actually work for what you were assigned to do, then you have to redo everything. So
Happens all the time. All the time. And with respect to just a little bit, I want to make sure that you guys, the pressure vessels that you're using pressurized to 3,000 PSI, that's pretty high pressure. Do you have a test program that validates the structural integrity of the vessels and?
the vessels themselves, the 3,000 PSI air tanks, we're just going to trust the manufacturer on that. The thing that we have to modify with the tanks though is that regularly they output about 800 PSI, so we will have to modify the tanks to be able, there's a little spring inside that regulates the pressure that we have to replace in order to drop it down to 300. After that, we'll have to make sure that it's still working properly, but other than that, we're going to assume that they work properly.
Okay, any modifications to a pressure vessel?
Yes, sir.
You have to be really careful what you're doing. Okay, other than that, really good presentation.
Thank you.
I'd like to echo what the rest of the panelists said. Congratulations, you've done some very good work here so far. Really have just one question, and it's on slide 17 on the structural subsystem. Okay, I have a different 17 than you do. 37, sorry. 37. It looks like a 1. So you pointed out that very clearly your margins of safety are definitely well over-engineered on your gimbal base and your gimbal rings. However, the number you have for the shaft is substantially lower. Do you anticipate any issues with that particular number versus some of the others?
No, with the loads that we've applied to this model, we've already taken into account a large factor of safety. That's added onto the max dynamic loading that our system, that our simulation is outputting that our system will have to take. And that number is a margin of safety, so which usually we would like to design to a margin of safety of between 0 and 0.1, but everything else is just really high just because we don't want it to just break. We want it to minimize the deflection that it has so that the friction is as low as can be.
All right.
Does that answer your question?
Yep. Just a quick comment though, looking at the gimbal, based on the sounds it is making, I recommend some WD-40 on that. And then bonus question, who designed the CubeSat that you're using as your model?
Actually, the CubeSat belongs to Dr. Benavides. We will actually be manufacturing more CubeSats to spec for the actual tests, but that is not something that we made.
I know the question was who, because I designed that.
Oh, I was going to say, we have the design documents from, I believe it was your team, EagleSat. We have the design documents, we're going to build our CubeSats based on those specifications.
Better answer.
Sorry about that.
Thank you, nice job.
Okay, so very nice job. Very good presentation, very professional. Congratulations. Page 26. My question is, can you give me a little bit more details on how you designed or selected the bearing for this support?
Sure, that process was actually, there were several iterations that we had to go through of changing this. However, I would like to pass this off to Gavin Hofer, because he can give you a lot more detail.
Yeah, so first from the simulation, we actually calculated all the expected dynamic loadings on each of the bearing. That accounts for all rotation, center, mass offset, all centripetal and linear accelerations, as well as gravity. From that, we determined both the radial and axial, the maximal radial and axial load components on every set of bearings. And so the bearings we're looking at are deep groove ball bearings, and based on research we found we want to limit the axial load to less than or equal to about 10% of the static load capacity for radial loads. So we had to find these ball bearings we're looking at have a static load capacity of 1,000 pounds. So they should be able to support approximately 100 pounds in axial load without damaging the bearings. Does that answer your question?
Excellent, yes. The other question I have, oh yeah, you can keep the mic, I guess. The other question I have is, you have a proper way to assemble it for the inner ring. Now the outer ring, you mentioned that you are going to do press fit instead of doing, shoulders, and why do you choose to do press fit, and do you foresee any issues with that?
So the bearing is actually press fit into the, so are you talking about the gimbal base here? About this part?
Well, I'm talking about
okay.
the outer ring of the bearing press fit into the hole. Yeah.
So all of the bearings are press fit into their own bearing plates. The difference here is the bearing plate is welded onto this shaft, welded onto this structure. The reason we chose press fit, we did a lot of back and forth with the technicians at the machine shop here on campus, and it seems like that's the best option. That way it'll hold it in place, because we don't want the bearing to move at all while it's in there. And press fit was the best option for that. And also the bearings never have to be removed once they're inserted. The shafts are not press fit into the bearings. They can be pushed in by hand. It'll be a close fit, but you'll be able to push them in by hand and remove them.
The reason I'm asking because press fitting the bearing is very difficult. It's a very difficult fabrication process because you have to really be very, very precise because if the pressure is too high, you end up creating friction in the bearing. So I see that you have worked a lot on that, so very good. Page 34. So can you comment on the location where you see the maximum stress and why you see the maximum stress there?
Sure, so the person that did all of that analysis is Drew Takeda, and I'll pass it off to him.
So the location of the maximum stress occurred right against the bearing plate on the shaft and the inner gimbal ring.
Okay. So those are stress concentrators.
Yeah.
Did you think about removing those stress concentrations using fillets, and did you simulate the welding that is going to be on the structure?
Yeah, so we plan on having shaft collars along the shaft next to the bearing plate, so that will help reduce and spread out the stresses. And also the ends of the shafts on the inner gimbal ring will be inserted into flange collars on the satellite, which will help reduce the stress concentrations as well.
Very good, excellent. On slide 46, can you comment on the friction force that is going to be between the lock mechanism and the CubeSat? And if you did any evaluation on that to dimension the power required by the solenoid to pull that locking system?
We will have to get back to you on that question in particular, but just right now the lock style solenoids that are holding that in place will have to be very securely fastened to the mounting plates that will be on the opposite sides of the CubeSat housing, because there will be a pretty significant force exerted from the CubeSats.
Excellent, very good. On slide 54 and 55, so 54 you speak about the X, Y, Z angular speed. Are those the components of the angular velocity vector, or are those the derivative of the three Euler angles theta and psi?
Those are the components of the satellite. So the rotation of those will rotate with the satellite. It is a derivative of the Euler vector. However, it won't be calculated like that because we'll be calculating it through using the IMU.
Yeah, yeah.
It looks like,
Sometimes it's confusing because if we speak about X, Y, Z, someone could think about the frame, the inertial frame. So the three components of the omega vector in the inertial frame rather than the derivative of the Euler angle velocities.
I'm going to give it to Gavin again.
Yeah.
Those values are the components of the omega vector.
Oh, okay, good, excellent, very good. Now on 62, just very picky comment, but so what is the units of power? What are the units for power?
The units for power for,
In general, if I ask you what is the SI unit for power?
it's joules per second.
Yes, so it's a derivative on, so now watt hours, joule per second, which is a watt, okay? Watts are joule per second. Watt hours are actually a measure of energy, not of power.
Okay.
So because it's the integral, if you have watts and you integrate with respect to time, then you get watts hour. So
Okay.
that is actually a measure of energy, not of power.
All right, we apologize.
No, I mean, very picky comment, but just, now on slide 70, you mentioned that you have a second mock-up coming up.
Yes, sir.
What's the purpose of that?
The purpose of the second mock-up is just in case we have any design changes to this mock-up.
Okay.
We will be keeping this mock-up, however, if anything, if anything changes, we have to modify that before we present on the final product.
Okay. And the last question is on slide 71. So if we divide that by 10 and by the number of weeks, like 14 hours per student per week, does that include class time or not?
That does include class time, yes.
But still is and 6 hours of class time plus additional 8 hours every week on.
Yes, sir.
Wow, that's pretty intense. Very good job. Congratulations.
Thank you.
Great, thank you. And our next presentation will start at 1:15.
Okay.